We're going to leave Lewis model behind or set it aside and talk about a more advanced model called valence bond theory. The Lewis model is an oversimplification. We know that. But the awesome thing about it is that it works a lot of the time. More advanced theories apply quantum mechanics. So they're going to more accurately predict a lot of the properties of molecules that we observe. Bond length, the strength of the bonds, the geometries, the dipole moments. It's going to explain some things that Lewis theory can't handle. We're going to look at two of these more advanced theories, valence bond theory and molecular orbital theory, in a qualitative manner. We're not going to do the calculations because that's very, very advanced and we don't need to. We just need to understand the overall idea of these theories. So valence bond theory treats a chemical bond as being an overlap between orbitals. So just a review in case you've forgotten. The quantum mechanical model of the atom has electrons residing in orbitals. Those orbitals are localized on individual atoms. We've got the s, p, d, and f atomic orbitals. They have their different shapes, right? And valence bond theory says that we can hybridize the atomic orbitals to make different shapes. So you can take an s and a p orbital and combine them together and you'll end up with a different shape. This visualizes bonding as when two atoms approach each other, the electrons and nucleus of one atom are going to interact with those of the other atom. We're going to look at the energy change resulting from those interactions. A chemical bond will form if the overlap, if the interaction results in a lowering of energy. If it results in raising the energy, a bond will not form. Everything's going towards lower energy. So let's look at two hydrogen atoms. So two hydrogen atoms, they each have one electron. That electron is in an s orbital, which is spherical. So here we have our two hydrogen atoms and this electron cloud representing the density of that one electron. So out here, as they're approaching each other, this here is the distance between the atoms. And on the y-axis, we have the energy. So high energy is at the top and low energy is at the bottom. And if you look at this red line just as like a hill and think of, well, if you were rolling a ball, where would the ball end up? It would end up at the bottom, right? At the lowest energy point. That's what's going to happen with these atoms too. So out here where the atoms are separated, there's a little bit of attraction between them. And so the energy is slightly lower than zero as they're approaching each other. As they get closer together, the electron from one is attracted to the nucleus of the other and vice versa. And so the energy gets lower. And we get to this sweet spot here where we have the maximum attraction between these two atoms. And then if we get closer together, then the energy starts going up. So we can think of this in terms of people too. If you're really, really far away from a person, you may not even know that they exist, right? You get closer to them, you meet them, you're like, hey, I like this person. And then you get closer and you talk, right? But then there's that personal space issue, right? And if you get too close to someone, they're like repelled by that. They're like, hey, wait a minute, I need my space, right? So you can think of this as two people. They're coming together. There's this ideal spacing where you can talk and interact with each other. But if you get too close, that's not good either. Does that make any sense? So this is the predicted bond length for a hydrogen-hydrogen bond. It's the distance between the nuclei when the energy is at its lowest. And this is the bond energy. So by getting together like this, their energy is lowered this much. The bond is forming. And so in order to break that bond, you're going to have to exert this amount of energy to overcome that. So that interaction energy is generally negative, meaning stabilizing. More negative is more stable. It's going to be negative when the atomic orbitals of those individual atoms they each have one electron, so that when they overlap, they can spin pair, because individual electrons are going to be repelled by each other. But we learned when we talked about the orbitals and how they pair up, that if they spin pair, where one spin has a positive spin and one has a negative spin, then they can stabilize with each other. So usually what happens is the electrons in that stabilizing orbital come from two half-filled orbitals, meaning each atom contributes one electron. That's what normally happens. But sometimes you can have one atom providing both of the electrons. And that's called a coordinate covalent bond, where one atom is providing both of the electrons in the bond. So when we have two atoms with half-filled orbitals and they start to approach each other, as the orbitals overlap, the electrons align with opposite spins, and that's what forms the bond. Any questions? So, summary of what we've talked about so far. The valence electrons for atoms in a molecule reside in quantum mechanical orbitals. Chemical bonds result from the overlap of two half-filled orbitals, and the electrons in those half-filled orbitals form a pair, a spin-paired set of electrons. The geometry of those overlapping orbitals is what determines the shape of the molecule. So let's look at H2S. So H2S, we can draw its Lewis structure. It's going to look like this. And from Vesper theory, we could predict what the shape of that is. But let's look at what happens when we think about overlapping orbitals. So here we have a hydrogen, and the hydrogens, we're just looking at valence electrons here. The electron diagram, the orbital diagram, for hydrogen would look like this. We have one electron in the 1s orbital. The other hydrogen also has one electron in the 1s orbital. The sulfur has a 3s orbital that's full and a 3p orbital. The 3p orbitals, one's full and two of them are half full. So we can have overlap between this half-filled orbital and that half-filled orbital, and overlap between this one and that one. So here in this odd balloon drawing, right? It looks like some crazy balloon art. What's going on here? Well, here's the sulfur. The blue sphere here is the 3s orbital, and it's full. So we've got two little arrows in there. And then the red ones are the p orbitals. So we've got one going up and down, and the other two are perpendicular to it at right angles. This one originally had one electron. This had one electron. The one that was vertical had the pair. Right? So we've got the pair, and then we've got two that are half-filled. These two that are half-filled are overlapping with the half-filled s orbital from the hydrogen. So this one's overlapping, and this one's overlapping. You see what the picture's trying to show us? So this predicts that bonds will form. We'll have H2S. This predicts that this angle, though, would be 90 degrees, because that's the angle of the p orbitals, right? So the actual bond angle is 92 degrees. Valence bond theory predicts that it's 90 degrees. Vesper theory predicts that it's less than 109.5. Because when we look at this, we see four groups. We see a tetrahedral electron geometry. Two of those are lone pairs. And so Vesper theory says this is a bent molecule. And because of the lone pairs, the angles are less than 109.5. So things are going okay here, right? They're not exactly the same, but they're pretty close to each other, right? Any questions about that?